All right. It sounds like you guys have some idea about what radioactivity is, what nuclear decay is. So we'll talk about this today, and this builds upon what we talked about in chemistry. So when we were in chemistry, what part of the atom was responsible for atoms interacting with each other and bonding with each other? Ella? The electrons, specifically the outermost electrons. Okay, and that's what determined which elements bonded with other elements, the properties of an element, and so forth. When we talk about nuclear energy, we're not talking about interactions between the electrons. What do you think we're talking about? The nucleus. That's why it's called nuclear energy, because these changes, this energy arises from the nucleus of an atom rather than the electrons. So remind me, what is in the nucleus? Ditya? Protons and neutrons, correct. Protons and neutrons are the particles that are found inside of the nucleus. This all should be easy, right? We just had a quiz on this. What is the charge of a proton? Raise your hand. Elizabeth? Positive. So if you know about the attraction between positive and negative, or poles in a magnet, what should two positive charges do, Abby?
Repel each other?
They should repel each other. Just like if you put the north pole of two magnets together, they repel each other. If you put positive charges near each other, they repel. So that's sort of weird, because the nucleus has all these protons in it, which are positively charged. Why doesn't it just repel and explode? It's because of the neutrons. The neutrons sort of act as glue between the protons, holding the nucleus together, even though most of it is positively charged. So, the more protons there are in a nucleus, what do you think that means?
Neutrons.
What?
More neutrons.
The more neutrons. Okay? Which makes sense, because as you look up the periodic table, if you look at things with a atomic number of 7 or 8 or 10 or 20, they have larger numbers of neutrons in them than some of the lighter elements. But for some elements, their nucleus has so many protons that even those extra neutrons being added are not enough to stabilize the nucleus. So most of our radioactive elements are at the larger end of the periodic table with a higher atomic number. I should mention now, because I see some of you looking for it, you will need your periodic table throughout this whole unit. You're going to have to be referring back to it. So you might, if you have it handy, take it out. So do you remember the term isotope? Raise your hand if you could tell me what an isotope is. Colin?
It is like a different version of an atom, and like so it'll have like more proton or more neutrons in it than one of like the most stable one, and they have more or less.
Yes. So it is an atom of a certain element that has a different number of neutrons. Could it have a different number of protons?
No.
No, because that would change its identity. These were common questions you guys got wrong on your chemistry quiz. And many of you did not make the connection that it's the number of protons that determines the identity of an element. So yeah, an isotope is an element that has a different mass because it has a different number of neutrons. For example, I'll let you write that first. Here I have 3 isotopes of carbon. carbon 12, carbon 13, and carbon 14. Carbon 12 has 6 protons and 6 neutrons, giving it an atomic mass of 12. That's what the numbers are. Carbon 13 has an extra neutron, so it has a mass that's 1 greater. Carbon 14 has 2 extra neutrons compared to carbon 12. It has an atomic mass of 14. And different isotopes often become unstable. That sort of balance between protons and neutrons is not in balance, and therefore it becomes unstable. And when a nucleus becomes unstable, it often will eject a particle and energy to get to a more stable configuration. So we are going to talk about 3 different types of radiation, nuclear radiation. Alpha particles, beta particles, and gamma rays. And so when a nucleus is unstable, like we just said, it can eject a particle or energy. Sometimes it might eject what we call an alpha particle. Does anyone remember when we've talked about alpha particles before? Tyler?
When they shot them into the glass?
Yeah.
No, not the glass.
Who shot him into the gold foil? Remember his name? Mahmoud?
Ali.
Ali?
No, Rutherford?
Rutherford, yeah. Rutherford's gold foil experiment, he was sending alpha particles through a very thin layer of gold and seeing what happened to them. So an alpha particle is really a helium nucleus. That's what an alpha particle is. If you look at helium on your periodic table, what's in its nucleus? Mattis? That's hydrogen. Helium. Abby?
2 protons and 2 neutrons.
Yes. It has 2 protons and 2 neutrons. So what we do when we are sort of writing out the symbols for an alpha particle, this is what we write. Helium, He, 2, because that's its atomic number, and 4 because that's its atomic mass. Now alpha particles are actually really large compared to other types of particles that are released during the breakdown of radioactive elements. They can be stopped by just a single sheet of paper and block an alpha particle. Our skin can stop alpha particles from penetrating into our body. Beta particles are basically an electron. They have the same mass and same charge as an electron. That's what we call a beta particle. So, are electrons larger or smaller than other subatomic particles? What do you think? Abby?
Smaller.
Much smaller, yeah. So a beta particle is when a nucleus breaks down and ejects from the nucleus an electron. The symbol that we use when we're illustrating a beta particle is an E, which stands for what?
Electron.
Electron. What is the mass of an electron?
0 AMU.
0 AMU. And -1 is what we use for its atomic number, or its charge. Now this may leave you with a question, because what is in the nucleus? Neutrons and protons. And what am I telling you can be ejected from the nucleus? An electron. Well, does that make any sense? Not really. Here's the explanation. When we have a neutron, and the nucleus is going through this beta decay, the neutron releases an electron and becomes a proton. Because the neutron, what kind of charge does it have? No, neutral. It releases an electron, which is a negative charge. So what does it become? A positively charged proton. So that's how you can get an electron out of the nucleus. A neutron becomes a proton. Beta particles are much smaller, much more energetic. They can penetrate into objects a greater amount than an alpha particle. They can be blocked by a thin sheet of metal. No?
How would you like get an alpha particle like Rutherford? How is he able to like take?
He had a radioactive. He had a radioactive element inside of his little case that was decaying. And that radioactive element, when it decayed, released alpha particles.
Okay, so I thought like when it said he was like shooting alpha particles, I thought he had like a little like squirt gun.
No. You have a radioactive element substance in there that's ejecting alpha particles. In the experiment we saw in the video that was a recreation, he used americium, which is a radioactive element. Sometimes it's found in smoke detectors. If you ever look at a smoke detector carefully, it will tell you that there is a radioactive substance in it. Okay, that's how it works. And radioactive substance in most smoke detectors is americium.
Like, how would we get the
That was, oh, basically you could gather natural sources of metals and ores that are radioactive, and you can find them. All right, and then our last type of radiation is called gamma radiation. Gamma radiation has no charge and no mass. It's not a particle. It is basically energy, very, very high energy. And it is very, like I said, very high energy, and it can penetrate into substances the most out of any of these types of radiation. In fact, it needs a thick piece of lead to stop it from penetrating. Has anyone had an X-ray anytime recently?
Oh yeah,
Okay.
my hand back.
So, what do they put on the parts of your body that they are not X-ray?
The big like
Big, heavy,
Yeah.
like blanket.
Yeah, it's like yeah.
What is that made out of?
Lead.
It's made of lead.
It feels so soft.
Why do they put it on you?
So you don't get all the extra radiation.
Because the radiation penetrates where? If they're X-raying your tooth,
Yeah,
they want the radiation to go in to your mouth to make the image. Or if they're radiating, your shin because you broke your tibia. Okay, they want the radiation to go in there. That's what forms the image. But they don't want to expose any other part of your body to this high energy radiation. Because what effect can this high energy radiation have on our cells?
radiation poisoning.
It can cause radiation poisoning. It can lead to increased incidence of skin cancer, or of cancer in general. So not by having a single X-ray, but if you get repeated exposure to X-rays, you can be at a much greater risk of developing certain types of cancer. In fact, the very first researchers that studied radiation before they knew anything about it, actually nearly all died of radiation poisoning and cancer as they got older, because they didn't know they were exposing themselves to dangerous energy.
Marie Curie.
Yeah, Marie Curie is an example. And we're going to watch a video about her. Or tomorrow, or
There's
maybe
a
next
guy,
week.
you should watch a guy named Veritasium.
I've seen it. So radioactivity, so different elements are radioactive, Typically, they are things that have a larger atomic number. There are some that are, like we said, carbon-14 is radioactive, but most of these elements are the larger elements. So this chart sort of shows an example. The green elements, okay, are some that are relatively stable for a radioactive element. They do break down over time and decay, but they have a half-life, and we'll talk about what that means next week, in the millions of years. So they're not rapidly decaying. They're fairly stable. Okay. The orange ones are a little bit more radioactive. They have a half-life on the order of thousands or hundreds of years. Okay. Red and purple are the extremely radioactive, the extremely active elements, where they have half-lives and they're measured in days or even less, and so they're breaking down very quickly. So it depends on sort of the size of the element, which is often what determines how stable it is. How?
Say there's like just a piece of,
There's just a piece of.
there's just a piece of normal radioactive.
Oh, I thought you wanted me to say it. Go ahead.
In just like nature, like in a cave or something.
Yeah, it happens.
Will it break down by itself,
Yep.
or does it need something to
Nope,
expose it?
they break down just naturally. It's just part of their instability. Yep.
So, well, like, say if they're exposed to something else after they got broken back, the ones that they got broken down, would they ever be able to form back
No.
together again?
So this is an illustration showing sort of how energetic these particles are, because alpha particles are not very energetic. They just get blocked by a simple piece of paper. Beta particles, a thin sheet of aluminum can block it. And gamma rays can go through both of those. They need a thick layer of lead to be blocked. And we actually can count radiation using a tool called a Geiger counter. If you ever seen maybe a movie and stuff, they make like a clicking noise every time they're sort of exposed to a radioactive element, and so it helps you detect that radiation. So they use it in the flash. Yeah, and it starts more and more as it gets closer to radioactive source.
Cisco.
Yeah.
Cisco. Oh, Cisco.
All right, I guess we'll go to talk about Marie Curie and move on talking about radioactive breakdown and transmutation elements. We'll do start with that next week.
I really want to watch it. It's a drama life. I really want to watch the potassium video. Because me and Ashley are trying to decide if you